So, good morning, Norway. Tak for having me. I'm not sure if you say it like this. It's my first time in Norway. I just arrived yesterday. Some adventures. It was a journey in itself. I will talk a bit about it, but it's all related to me. Uh, but the talk is about us at TP building our web services on our backend fully in C++ and pouring in some Rust at some point. But basically, we're showing how we did everything with C++ to get a web service running, how to get to scalability, all the difficulties we had in the team to argue about the architecture and so on, and a bit showing you what we use for tech and how we solve things basically there. So we have a small team that is growing. There are some more interns and so that we hope we can hire at some point. But for the moment, we're like 6 FTE, full-time people. And we have a very strong focus on C++. But also have people that can do Rust in the team. And also, happily, we have Valentina that is also taking a step back and looking a bit at what it looks like for users, because us as developers, we are more like interested in code lines than in user experience sometimes. Oh, by the way, just as I said, I broke the screen. So what we do at TP, mainly remote C++ builds. And that means we do actually remote CMake builds, which in turn bring us to allow remote Rust builds as well, via CMake basically, without changing anything to the Rust code base itself. It's very well integrated. The logo comes from a project that helps us in that direction. I will speak about it later. The thing is, I'm in a C++ conference, right? And I love C++. I'm a Boost Fusion contributor and so. So disclaimer, this is not about this. This is not about the Rust evangelic task force trying to say C++ is so bad, C++ is unsafe, and so on. I disagree with that. I think C++ can be safe, and I think also there is things that need to be improved, but I also think that it's good to be able to mix things. And so, no, don't rewrite it in Rust. Perhaps some stuff you can write them from scratch in Rust, but don't do that because you will just generate new bugs, the same you had in C++. And yeah, but yeah, it can be fun, sure, to learn the new languages. But then the question is, why remote builds? Why do we need that, basically? Why do we even care? And why did we build that service for it? The reason is we don't want people to compromise, actually. Because you always basically have in your build pipeline the choice to do a lot of checks and have a very slow build, slow release process, but have a safer build, have a safer, more static analysis and so on. Or to build very fast in release mode with optimization on and just don't care, you know, and ship it to the customer to see. And I think we can avoid this compromise if you have enough resources available. And one of my example that I have today is using a project which is named Sanitizer CMake, and that allows to basically add sanitization to your build. But before I speak about it, I will look at the code. So when I arrived in Norway, I don't know why, I was probably pretty tired, but on my way to the Zurich airport in Switzerland, I forgot my luggage in the train, but I thought about it and I ran back and I took it with me. And then when I was in the train between Oslo and Kongsberg, imagine what? I forgot my luggage a second time. But this time I didn't thought about it. I was just thinking, wow, it's so cool, Norway. Oh, it is like this. And it looks like in the video game where I played in some Norway things and so, Norway landscapes. And then suddenly I had a meeting with users and with the team. And at some point at 5 or so, I noticed, by the way, I forgot my luggage. So I think my brain is not implemented in proper C++, it seems. It seems it's implemented in old C code without error II, without resource aggregation is initialization. And I don't know if you can spot the issue here, but basically we are having a list of tasks, of things to not forget. And one of the things I should not forget is taking my luggage when leaving the train. So in the meantime, I bought some clothes because otherwise I would have been very ugly today. And I just had my my clothes for travel, and I thought I would have time to go to a barber or so, but sorry, you have me like this. And actually, here we are basically doing a use after free, but it's not easy to spot, right? And what is cool is if you enable a memory sanitizer, like if you run with a toolchain file that allows this, for example, here build on macOS with memory sanitizer, then you can get out of your build and test execution basically the information that you got use after free, and you can also click where it was. Like here we have this format library that is used. But basically, if we get here, we see there was the delete that was done earlier, and it was initially allocated here. And actually, all these tools are available in C++. And we have the UB sanitizer, which also catches a lot of bugs early on. First, I can unzoom a bit. Here, if we take an integer that we overflow, this is a UB. And actually, if you would like to notice that you are not doing any mistakes, basically you can also build for macOS, but with sanitize UB, which is what is sad is you cannot run UB sanitization and address sanitization in the same build. Like the two instrumentation are not compatible, and there is also a performance impact. So you need to do another build again. And this is where I say we have a tendency to compromise because on safety, because then you have to build 3, 4, 5, 6 times. And what you can see here is that it caught that we incremented a bit too much the int, and that is actually overflowing. And this could not have been caught at compile time because argc is a runtime variable that is given to the main function at the beginning. And so with these tools, we can actually get a lot of the safety that the Rust people say, oh, it's unsafe, it's unsafe. And I think if you combine both, and if you also bring to use that in Rust, because in some nightly build of Rust, they start to allow to use address sanitizer and so. So if you combine both, you can also have it over boundary of your C++ and your Rust, basically. And that starts to be a very safe world. And what we want to offer basically at TP is to offer this experience, but that every time you type something, you can get all the the checks that you get from this sanitizer, but also for your different cross-platform build, that you get them every time you write something. So if here I will just put an additional line, it just rebuilds, and I again have the check running here, and I have multiple times the UB here. And what is cool is that in principle you can run in parallel sanitize UB, sanitize memory, and so on. And that's why I think remote builds matters, and that's why I think we should not compromise on safety. The idea is to bring your CI to the fingertips, and you don't get any bugs in production then, because you had all these tests running on your end when you were typing, and you don't wait on your CI workflow. You don't like push and then get back to home and then get a mail, oh no, my build is not finished. You already changed context, and so you want basically the result immediately. So no, the thing is we have to make that available, right? It's not like remote builds and it's there. So how we did that at TP is I argued with my co-founder Yannick, who is a kind of a polyglot, also a lover of JavaScript, sadly. And so why compile languages for C++? Some might say it's masochism, like it's not easy, you don't have the tools, and so on. Actually, it's not true in my eyes, and I can express myself way better in C++, and I feel way safer, like having something that compiles and tell me that I forgot something in the syntax or in the method resolution when I have that at runtime, being said way later when it's the user clicking on the button. So I think it's not, but yeah, sure, when you get a lot of error message and when you usually use just to save a JavaScript file, is not like the same and can be considered a bit like masochism. But no, there is a serious reason for this. For me, internet is also a generator of CO2. I spoke to people that are doing carbon capture, so it's, oh, it's nothing. But if you just take, not the video, not the audio streaming, you just take basically all the PHP website on the, like the top 10 million websites online, and you just take like requests that are sending text over, or that are doing parameters, you are basically having 47,000 CO2 tons yearly emitted, if we consider they all run on typical most sold Dell servers and so. And I think we can do something about it. You have some responsibility as software developer. So better use that when we build, not when every time a user clicks on the button. If you take a simple web services that is doing some database request and replying with formatted in JSON, you can find it on this Tech Empower web framework benchmark. It's all available with a lot of frameworks, C++, JavaScript, and so on. You simply need 7 times less server to serve the same amount of requests with C++. So all this scalability topic and so that you have for a startup at the beginning, you say, oh, I have to write it in a way that it will be scalable for the day we are successful, basically. Actually, you don't care because you can already just, if you write it in C++, you can already serve 43,000 web requests per second, doing JSON generation, PostgreSQL query behind. Whereas to do the same with Python or PHP, you need to basically deploy 7 times more servers. But that leads us to the first part of our journey with Yannick. It's like my co-founder. He said, like, yeah, we should do microservices all the way down. I'm like, no, we cannot. It's too complicated. If we do that, we'll just be stuck, like writing code to synchronize the state across the microservices, and we don't have teams to write each of the microservices. So yes, monoliths are not so cool because they don't scale that easily horizontally. Yeah, I mean, but you don't know before you have the performance issue, before you could measure a hotspot, where you have to put the microservice actually or where you have to separate things so that you can get horizontal scalability. You can have availability issue if you have a monolith. What I don't like with microservices is that it tends to be Conway's law, basically. Like, I am the person, or we are the team writing this microservice, so we do everything in our world, and the way we communicate with this other team is going to be the API, the REST API, or whatever API you are going to have between the microservices. In theory, it forces you to design the app in a scalable way, but how can you know where are your hotspots before measuring? And that's why I think you should have the choice at deployment and not at compile time. Like, you should have the choice, not when you write the app, but later on to modify it easily to move to microservices. Sure, monoliths you can also scale for a while with big servers. It's also what we do for your builds. When you do a remote build, we give you like a very, very, very big machines instead of splitting things up. Because that way you don't have the synchronization overhead between the nodes. So you get also faster builds, but you are limited. So at some point we reach the 500 cores limit of our cloud providers, and that's it so far. But we do caching and so it can be solved. We use a web framework that is named OATPP, and the author of this web framework, which is a C++ framework, has coined a term that is named monolithization. And it actually means that you can write each of your microservice architecture like you would usually do with a class architecture, like defining the different services, and just have a build that differs, like you build it once as a full executable statically linked, and you build it as library. So that if you need to scale and you need to have multiple instances of the same service, you can decide just by configuration to run the app by loading the libraries instead of running the app by loading by recompiling the executable, rewriting everything and so. And I find that very cool. And you can see that Here is the number of requests served by seconds on the vertical axis, and you can see that basically the monolith is usually faster to serve requests when you are in the lower end, but at some point you outscale you get actually to the load of the server. So if you reach to the load of your server, you need to go to microservices to some end, but you can just configure that basically. On C, monolith is better, but so we have a compromise at TP in the terms of what we do as microservice, what we do as monolith basically, and we try to apply that in our code base. So as we did everything in C++, we said like reinvent all the wheels because there's not that much people doing websites in C++. I mean, there are big websites like Google, but we don't have access to the web framework. So what we did is combine a bit of text. So we have some JavaScript for just to bash a bit JavaScript. The JavaScript service is rebooting like every now and then, like every 2 weeks or so, or something, and it's leaking actually memory. And the C++ service, it's just like 6 months uptime, no leaks and so on. And we wrote that with the worst situation possible. We were super stressed. We had a lot to deliver to users that were waiting on us, and so on. So C++ can be safe, and we use Docker swarms and TP itself to build TP because we dog food everything. It's very important. I really think that in our team, we are not like in this team that is saying that, oh no, we should use a product. We use them. It's sometimes hard because building a tool that builds your code, that is a tool to build, is kind of recursive, but it's manageable. We did it, and we continue to do it for everything we do. It sometimes brings you to a blind spot because you find workaround because you know the tool well. So you think, oh yeah, this is solved, but it's not. That's also dangerous with dogfooding. But generally, we notice what the user endure and we know where to fix things. So this is a TP deps file. This is just to show you how to build a C++ web application with OAuth-PP. So you can actually depend on OAuth-PP in another way. This is just I'm used to using my TP for the dependency management. So here I also added the Swagger to it. Basically, an application is like kind of a boilerplate code to send you to a controller. There is some macros. There are some. I mean, I've been contributing to Boost Fusion, so I like a lot of macros. I'm not saying it's the best thing to do, but it's sometimes helpful to do cool things. And actually, super nice to generate Swagger on the OpenAPI REST API. So basically, you just define your endpoint with this macro endpoint info. This is for the slash, for the root of the website. You say what is the documentation of it. You say what is the response type expected in case of a successful request. And then you can basically return what is named the DTO. And the DTO is basically a data transfer object, which is kind of the way this framework basically allows to automatically deserialize JSON or XML or whatever. And if you want to build a web app with C++, it's pretty cool. You just do this. And test jobs is just running one web service at a time. And every time we change something, it rebuilds. So here it's now saying it's listening on port 8000. So we can get here, we get that hello world. But because we have this Swagger that is automatically generated, we can directly see the documentation of our API. And we can naturally try it out here, execute, and that's basically it. You have a web service in C++, and I can guarantee you that scales well. And if you want to add one endpoint, it's just like you add another controller, or you add one to this and say NDC, and let's just say NDC here. Just save it, recompile, and oh, what did I do? So what did I break? I did something wrong. Okay. Oh, I think I copied. Yeah, I'm missing the endpoint info in that regard. I just copied the and I duplicated actually root, which is, yeah, I need to give him a type name that is valid. Okay, so yeah, he wants to listen on my, and so suddenly we have get NDC, and we can try it out, and we get the message as well, NDC get back. So this is available if you want to look at it. There is some boilerplate code in the to start all the components. It's just like a main function with like 20 lines. I don't think it's necessary to look at it together now. And now let me show you like an overview of how this framework is used inside the tipi.build website and where it lands basically. So we have this Docker swarm, which we can host anywhere, and we are kind of multi-cloud capable. That means that in our C++ web service that is here, like this big monolith, we have actually implemented a lot of cloud APIs, so that whenever someone wants to do a remote build, we actually create on the cloud vendor that is fitted for it the actual machine, and we build the data there. So we had to do some stuff, and I will get back to it later, to send the code only to these machines and not to our backend, so that we don't steal code of people and so that it stays safe and always encrypted and not in the facilities of TP directly. And we have a JavaScript web service for the authentication of people against GitHub or GitLab. GitLab is not rolled out yet, but it's being rolled out next week. So we basically use the typical libraries for that, and I thought it would be super easy, but it was harder to do Open API REST web service in JavaScript than it was to do it in C++. Like we had to build our own Open API library and so on. With WebPP, it was just like everything was there from the start, and I was amazed. If we would have used TypeScript, it would have been a bit better. We used JavaScript ES6, so yeah. But I really didn't expect that, and yeah. So C++ is great for web development. We have some databases like Postgres, and we will come to it, how we store data in it. And we don't do inter-process communication over the database, but we have some state of the machines and so that is kept there. And yeah, we have also a caching service for the code during the session, and then it gets dumped after the session of the build. So basically, when someone builds something, it directly contacts this machine for building, but it contacts first this service to ask for a machine, and this is deploying the machine, and then you get the IP basically, or the DNS address of this machine, and you directly contact it. So that's basically it. So I showed you already how to do that. This is just a summary of it, and you can, as said, add all the documentation there, and you can add security requirements to your endpoints and so. So it's also very nice to check if everything is like passing through the same authentication method and so. And when you speak about authentication, let's speak about how we handle actually password to access GitHub, Git cloning repositories, and so on. And for this, we actually use WebAssembly. So when you first log in on the website here, in your web browser on the tipi.build, we actually create a vault in your browser with a C++ code base that is open source, and that actually encrypts all your tokens to GitHub or to any source code hosting repository in your browser, and then it sends it encrypted to the backend. And so our backend never knows anything about your website, about your password for Git or GitHub and so on. The only who knows is your browser, on your local machine, on the machines that you use for the build, basically. But these get like just started during the build, deleted after the build, and it's hard disk encrypted, and there is encryption also over the wire. And so the code actually never leaves your safe space, basically. And this was a big topic. Also, Yannick is a former hacker, and he spent quite a lot of time on forcing us to go in that direction. I was like, no, we have to make a POC and so on. Say, no, security matters before all. And he was right. So this, when you look at this here, if I go to the website, to the TP website, and I sign in with my GitHub, this goes to API accounts, it gets back. Then if you look at the vault here, this is actually the JavaScript service sending us a blob that is encrypted, and this blob is getting decrypted with a WebAssembly code, which is hosted here. tipi.build vault. Oh, no, that was not what I intended to do. And basically, this is a very simple code base with a class that provides you the different kind of endpoint we can connect to, the different information, the password and so. And it uses crypto PP under the hood to perform the encryption. What is cool with that is that you can actually use it from your web service for your web page. PowerPoint. Here. Is that this API is actually usable from your web service when you use mbind. It's an header from mscript 10. It's also available by default in TP. When you build by default, it builds for WASM, and it launches mscript 10. You can basically declare all the function you want to expose to JavaScript. So you basically say, okay, I want the constructor to be this one, and then I want this function add to add a token to the vault, like a GitHub or Git token to a clone code. And also, like, then you can, there is a function to get the encrypted buffer out, because the only things that gets out are in that library from the perspective of sending it online. And basically in the JavaScript code, it looks like this. You do a new TP vault. There is an equal missing here. Sorry for the typo. Then you get the data encrypted, and we send it over update vault, which is like an open API endpoint. So this happens in the browser, and that means never no data leaves your no secure data leaves your browser or your local machine, basically. But then we have, as you have seen, I have clicked on sign in. I used GitHub to sign in, and I got basically a token. And for this, we use JSON Web Tokens. So JSON Web Tokens is a standard to actually say have between microservices have tokens that have expiration time and that can be refreshed if you have enough trust in the client. That are used to actually authenticate you across all services. So accounts generate this JWT, and API tipi.build, for example, validates them. And what we do is we use a library which is named cpp.jwt, which in turn uses element JSON and OpenSSL. We do use boring SSL instead of OpenSSL, but I know it's not FIPS and so, but it's good. We then have in the OED PP, you just need to have this bureau authorization handler added. And when you add the security requirement, then basically every time an endpoint is contacted, it expects to have this bureau token in the request. And then we can basically decode and check if the token is correctly signed. Here, there is actually a security issue in the actual code. There is more. It's just for the purpose. You have to check in the token has the right scope and if it's still valid, because it's just checking if the token is signed. So you have to have some if my token contains this scope and so on in there. But in the real code, it's not like this. You can try. I am happy if you try to hack us. And then we have database. So the thing is, a lot of web developers, they tend to use object relational mapping software. There is a lot of tools in Java. There is a lot of tools in JavaScript and so on. In C++, there are some, like there is ODB and others. But actually, why do you need one? That's my question. Things that maps SQL tables to classes. I mean, if you have the control on your database, I would say you don't need one. we just store object directly in the database. Like not C++ binary ABI objects. We use a small library that is relying on Boost Fusion. You can do that in many different ways, but basically we have on GitHub cpp.json. It handles like a lot of types automatically, and also some semantics for optional and so that is very interesting. And so you can have to JSON or from JSON just out of a type if you have enough metadata. If C++ at some point standardizes reflection, you can get rid of line 9. But so long it doesn't, let's skip with it. And for example, for the machines table, to know which machine is running and which cloud vendor, what is the status, should it be destroyed, should it be redeployed, or should it be reconfigured? We basically do it like this. We have a struct basically in our source code with the ID being generated from Boost UID, and have the cloud vendor type that we use for this machine, and which environment is being deployed, and how long we need to keep it alive when a user is running builds on it and so. And then we need to write a bit of SQL, which is basically always the same for all table, a JSON field, like a data field, which is a JSONB. And then we can also add indexes, because JSONB in Postgres, for example, is able to index on your data, and it's also possible to do special requests directly on the JSON data. And here it's OAuth again. You give a query, say the query is create machine, and you just do the insert, and we cast it in SQL as JSON from something that we get from our source code. And we could also store binary blobs, but that would be dangerous, right? I mean, it would be hard to maintain the ABI and so on. And when we need to change a field or so, we don't need to do database migration. We have mechanism in it, but I try to avoid that all the time. I'm trying to follow the fact that you have optional on a field that changes, that is no more in use. You just put it as optional, put the new field, and handle in your code the fact that there is things with this optional field that perhaps you need to check still. But it makes all the problem that you have, oh no, we are deploying the website, the database migration will break everything. You don't have them. If you tested your code on the database state, you just know it works. And this is the thing that the people at gRPC, Protobuf are using a lot. And that was my point. Why not take it for database? And actually, it's first it was like, oh, it won't be performant and so. And actually, it's as performant as SQL standard tables and so. It's even better in some cases. So then comes the point of, yeah, how do you send exception stack trace and so if the service crashes? So we have all this monitoring, we have a log monitoring, we have Grafana showing us stuff. I can show it basically. So we see, oh yeah, what is happening on the different deployment, if everything is fine, if we have enough storage and so on. But how do you send the actual exception and so on to the C++ developers so that they can fix bugs if that happens? So for this, we use Boost stack trace. And this is, and we basically, because our service, the web service, the backend is running exclusively on Linux. It also runs on Mac, and it might run on Windows for some part. We run machines for Windows, Linux, and Mac for builds, but the web service itself is on Linux. We basically register for the different signals that are very bad, like a segmentation fault, like null pointer, or memory alignment issue with SIG abort or so. And we basically use a signal handler to print the stack trace. And so we have at least a log, and also a small dump that is saved to it. But at the beginning, that we had that, we got a very strange error. Like, we got some issue, some null pointer. So the 6.7 handler was called. All threads disappeared except one. But the service was still replying, so it was still working. So we're like, what the hell? Like, we looked at the threads. There was only one thread instead of the 40 that should be there in normal idle situation. And it was super slow, but it was working. And at some point, after some hours, it stopped working, and it redeployed a new service directly. The swarm detected the application exited, so he started a new one. And actually, this was because we did not configure the build of the library correctly. So for each of the stack trace entry, it would like launch an external process to transform the address to a line that is readable. And this was so slow, even it was on a server hardware, even if it was because it was in the signal handler, it continued. And so the service was continuously leaving because the thread to handle the signal, when he was executing the process outside, he could continue his normal operation because signals are async signal safe. And yeah, that was kind of fun because we're like, what's happening? Why is it so slow? But at the end, it now even sends mails, and so in our case, so you can, if you can find a SIGSEV, you know, I get a mail and my phone rings very loud, and I always have my laptop with me so that you can fix things. But as said, we have 6 months uptime. This is normal like this. We don't have zombies in TP anymore. We track them all, and people will say rewrite it in Rust. But I say, no, we have 6 months of time with C++, so we don't rewrite it in Rust. It's stable. That being said, we had to introduce Rust because I promised I will talk about Rust at the C++ conference, which is very, very tough. Don't burn me. Don't send me flames. So who likes Rust here? It's quite a fair amount still, huh? Who hates Rust? Nobody. Only lover. Okay. And who prefer C++ over Rust? Okay, interesting. I won't say the counts. I will ask the ISO committee if I can tell. Just kidding. So the reason why we introduced Rust is that it's cool to be able to build on 500 cores machine. It's super cool if you can do that. But the problem is how you do that if you do just an incremental build. Like, yeah, your clean build is faster, but every time you do another build, you have to resend everything to the machine and to rebuild everything. So we basically had to add a strong cache for builds. And it's also very useful to speed up builds in general, to have cache and so on. So what we do to actually allow caching is that we have a system that is named tipi environment, which is basically just a CMake toolchain file containing all the flags that are basically defining your build, and that is impacting your ABI, which then defines if your cache entry is usable or not. And a Packer file, which is kind of a wrapper around virtual machines or Dockers. So by default, Linux build are on Dockers. If you do a Windows build on TP, it's gonna start a virtual machine that is provisioned with a script that is a Packer script that you can basically edit and that you can adapt to your own Windows environment and so. And so it's basically a way to define like the environment in which you build. And then if your local environment matches that one, you can reuse also cache entry that the cloud generated basically. And so basically when you start a build, we send always like in a small zip, the Packer file and the toolchain file on its hash, and then we deploy a machine based on this information. If it's already a machine that was generated or so, then we take that from the machine cache and so on, from the image caches. But that's basically the way you can add your own environment and like have an isolated, reproducible, hermetic build. Always have the compiler at the same place and so on. But then you have the source code of the people. And the source code of the people, sometimes it's on workspace DaminetReg on my machine. On the machine of Yannick, it's on home Yannick code. In Luc, we don't know why he codes in documents. It's very strange, but he has this code in documents. And the thing is, if you don't control your code base completely, you have like the absolute path to these folders. So you cannot reuse cache entry of one user or the other because it's in the wrong path, basically. So what we do is that we use Git under the hood, and we integrated Git very deeply in TP and in Ninja and so on. And we actually clone your workspace into a central location. which is either on Windows C, TP, on Unix is user local share TP. Then for each of the builds you do, we actually store a snapshot. And here it's taking the assumption it's a LLVM build because each LLVM builds are like 10 gigs build trees. And then we basically allow to rebuild on the nearest commit or on nearest change set. Also, if you didn't commit your change, we commit them for you in this mirror. The user doesn't see it; it just get built, and we have an hash on the content addressable cache entries so that we can refine that thing. So if one colleague already built that file in the same set or constellation, then we actually take the cache entry and just rebuild the difference on top of it. And what we do is that we need to restore the machine, the remote build machine fast, or restore your machine also very fast. Like let's say you want to do a fork on LLVM, you want to do a patch, you don't want to build LLVM, you just want to take the latest tag and have that restored on your machine so you can just edit and hack on it. And this is what we do with these cache packs. We basically rely on a Rust code base that we heavily modified. That is named elfchecker, and that is also using zstud under the hood. And basically, it's doing buckets of object files in the right way, so that you get the maximum compression. And like if you take 300 times 10 gigabytes build trees, you can get to 200 megabytes cache pack for all the revisions, basically because of the deduplication and so. And so that this deduplication works, we do it on a service on our end, so that you don't have to wait during the build process that this compression happen. We just send the snapshots and the service is doing that. And so it's there that Rust comes into play and we needed to integrate it. So it's open source as well. It allows to track each build snapshot by Git revision. You can also trace this object file comes from which sources and so. So it can also provide a lot of safety in terms of does that build really come from these sources. And it is a Rust code base in that regard. But it's very mixed with C++. We have a lot of C++ there too, because we have basically Git using libgit2, also very modified. Ninja and elfchecker together, so we basically merge them, and so that you can track sources on binaries, and that you can know what you have to rebuild based on the cache entries. And so we needed to basically get a lot of calls into Rust and a lot of calls into C++ from Rust. So we decided to use what is called 66RS, which is like a nice work in my eyes that did a lot of work to actually define the best ABI between Rust and C++. There is also people that found out that you can have C++ objects on the Rust stack. That's totally correct, and that's not a problem. And so it's a way to specify the boundary of your API in a very nimble and Rust and C++ native way. I really think this is the schema from the library author. Like they naturally said, safe, straightforward API, and here they say straightforward C++ API. I really think that actually both are safe or both are unsafe in my eyes. I worked on hardware, embedded hardware, and so that sometimes have hardware issues, and you can have whatever safety checks in your code. The hardware will do whatever you want with. So yeah, I think it's sometimes a bit overstated there. But it's very easy to use. We use a corrosion RS for that. It's a CMake module. So you basically say if you have a cargo build in Rust, which is the standard in Rust, you basically give in which cargo crate you want to build, and then you can use this add CXX bridge, so that allows you to basically build that bridge and build your mixed C++ Rust API. And if we take a simple example, you basically have, like, you may be used to the linkage specifier in C++ or in C, extend C, for example. So here the goal of this CXXRS is not to go back to C mangling, is really to get to the C++ ABI, sorry, on the linkage. And so basically if you want to expose a function in Rust, or if you want to expose a C++ function, then you do extend C++. If you do extend Rust, and you have all in the same module. And here we're just printing a C++ sent integer, as a 64-bit unsigned integer, with the lib print, which is a Rust function. And that just works. The header here, CXX bridge CPP lib, is generated by corrosion and by the tool. So basically, this code here, CXX bridge lib, generates a C++ header that you can use from C++. And so you can call into it. If you here is the example in question. We have that here, and you can basically build that, and then if you run it, we should see hello CXX bridge from librs. And yeah, that's it. And 136 comes from the C++. It's a C++ vector that is sliced for Rust, but you have different way to communicate over there. You can define types like native C++ types, native Rust types. And that means that basically you have you can use a C++ struct in Rust as if it was a Rust data type on the C++ side, and there is no copy happening unless you need a special type. And if you need a special kind of construct, there is a basic set of types that is defined. So you have like transparent types and opaque types, and you can basically also provide, if it's an opaque type, is a type that you didn't declare in the binding. So you can basically send a reference or a pointer to it, and you can also get access directly to vectoring elements from C++, from Rust, from C++ vector from Rust, and so on. And you cannot throw exception. It automatically gets calced into a result object and so. But it's very useful to build these bindings, and it's actually very safe. There is a lot of example on the website of the author. And if you see, for example, 60 strings, we basically have here a bridge object that is basically saying this is the header that I want to actually make available to Rust. On the types from this header that I need to be available in Rust, I define them as this. And then on the C++, on the Rust side, for example, you can call in to that C++ object, but the implementation is actually behind this is a C++ class that is using a stud variant and so on. And you don't have much overhead from that usage. And there is also a tool named AutoCXX, which is automatically generating these bindings for C++, which is made by Google. So I mean this one. So here you always need to write which function you want to export. There is a way to also automatically generate all functions from the header, basically. And so it's pretty cool to run things together. And you don't see much runtime overhead. It's not like typically JavaScript, C++ where you have to copy things around. So that was pretty interesting for me. And we are rolling out a backend including that very soon. For the moment, we still have C++ code on the official one, but you have the staging one that is already with that, and that some early adopter from us are using. So now, if you want to test the scalability of a website, I would say the best is you register on the website, and if you are among the two first to register, because that's always good for me, you can get one of these 2 chocolate boxes. If someone registers now or today, I will see it, and I will try to find you in the room, or if you do it now, you can get the chocolate. So thank you very much, and if there is any question, I'm happy to take them.